Hello everyone and welcome to our lesson number 3 on structural dynamics. Lesson number 2, we've covered about free vibration for undamped single degree of freedom system, and you can click the information card here. You can be able to watch that lecture there with some solved example, or just go down below in the description. You'll be able to get the links to our previous recording. This structural dynamic is a lecture series covered in 8 lessons. This is lesson number 3. So today we are going to see free vibration for damped cases. Next lessons we are going to see forced vibration for both undamped and damped cases. And as usual, this lecture series is brought to you by Dr. Gadeba Education Center in conjunction with Department of Civil Engineering at the Jomo Kenyatta University of Agriculture and Technology. And thank you for continuing subscribing. You can reach me on the address below here. Continue subscribing, liking, and sharing these videos as we continue learning together. Welcome. Last week, we found how to formulate the fundamental equation of motion for a vibrating structure, and that is general. The fundamental equation is general. Then we narrow down to single degree of freedom system. So even when we go to the multiple degrees of freedom, the fundamental equation is generally the same. That is Ft is equals to Ma plus Cv plus Ku. But now you may feel like we have a number of equations, not just one linear or one equation. We looked at free vibration. So remember how we were illustrating this. Don't forget this because these are our basics. What we said for a vibrating system, so when you apply externally applied force, which is F, which varies maybe with the time, it might be constant. Then we found that there are forces. One of them is the inertia force. The inertia force is represented here interior because it's because of the mass, so Ma. Then we have damping, Cv, C velocity, which is the first derivative of displacement. Then another force that we found is because of the stiffness of the system, represented by the spring, so which is equals to Ku. U here is displacement. By displacement now we are talking of, this is the direction of displacement, so the displacement will be U. So we'll be finding something like this notation or representation, showing that this direction of our motion on my screen was the right hand side. So you see these three forces are acting on the opposite direction of the externally applied force. And then we developed an equation. So for free vibration, the motion does not continue because of the external excitation. That is, maybe you apply a displacement. Let's use the simple example of a plumb bob or a pendulum, swinging pendulum. So if you apply the displacement, then you release it. The motion continues without the assistance of an external force. So again, you can just if not displaced, maybe you can apply just some force, but once you apply that force, you remove it. So the motion, so the initiation of the motion could be some forces applied, but when we come to analyzing the actual motion after time t is equals to 0, then no external force is required. That's why we are talking of free vibration. Then damp, we say that when there is no damping, this part, the Cu, the Cv collapse. But now here for damped system, now we bring back the damping coefficient C and the velocity V. Now again, if you look at this equation, remember the previous one, we said it was a second order homogeneous linear differential equation, ordinary differential equation. Still, this one is an ODE, but now it's no longer homogeneous. So, as you can see from the ODE that you learned, the previous we had said we had given some form of the solution, trial solution for the free and damped vibration. So for this case again, why we are just saying a trial solution here without saying where it comes from is because we are recalling, or we are recalling your knowledge that you learned in ODE. So this is the typical solution, a trial solution. And if now you factor the U to this, so first you need to differentiate once and then twice so that you can be able to substitute for acceleration and for velocity. And then you cancel common factor. By canceling common factor is, of course, when you substitute, when you differentiate this, you'll still be going to have C and the exponent. So they are going to appear throughout. So these are the factors that we are saying you're going to factor out, or to cancel the common factor. You're going to be left with this kind of an equation, which we call a characteristic equation. And the root, of course, now this is a quadratic equation. Remember, we have two roots, and this is the expression. Now the general solution, because we have two roots, of course, the general solution will be you see, this is a trial solution. So general solution is when we have lambda is 1 and lambda is 2. So that's why we are saying a superposition of the two roots. One root when lambda is 1, and then the other one when lambda is equals to 2. Now, of course, you know, see the values, see these are the constants which are determined from the initial condition. Based on the sign under the square root, we can have this value, whatever is under the square root, being 0 or being a negative. For example, if this part is larger than this part, or being a positive, is this part is larger than this. And that one gives us different scenario for vibration. So if the value is 0, then we talk of a critically damped system. That is, this component, K over M, and I hope you remember what is K over M. K over M, the square root of this is equals to omega, the undamped natural frequency. So when it's positive, we have an overdamped system, and when it's negative, we have an underdamped system. So let's see what this means. For critically damped system, it means the damping coefficient C is equals to C critical. So that's why now you see this part. So we are taking what is under the root. We are taking this part, which is under the square root. So the C will be C critical. So C critical over 2m, this mass, is minus, of course, this part K of M is equal to 0 for critically damped system. Okay? Such that you can be able to get the expression. Recall this, what I was giving you previously. So this is equation 11 from the previous slide. So critical damping coefficient is equals to, of course, if you make CCR to be the subject of the formula here, you're going to get this expression. Again, you can use this expression here to simplify further. So C critical is equals to twice M times omega, which is the same as 2K over omega. For overdamped system, we say C is greater, or the damping coefficient is greater than critical damping coefficient. So this term critical damping, meaning any value above that or equal to that, then it's like we have damped the motion completely. There's no longer vibration. There's no longer oscillation. Okay? So that's why we are saying for case A and B, for critically damped system and for overdamped system, there will be no oscillatory response. There will be no oscillation. There will be no vibration. So, and therefore, these two cases are not important for our analysis of our structure. They are not of concern. Okay? It's like when you say our structure, if it's critically damped or overdamped, it means when you just displace one, this is the initial displacement, which we call the U naught. Then you release the system, there is no motion, there is no vibration going to and fro. The system will just go back to its resting position. So this is not of interest to structural dynamics. So that's why we are saying we are not going to consider these two cases, A and B. One represent or illustrates what we mean by critical and underdamped system for single degree of freedom vibratory system. So you see, we would expect the motion to be like, if it was oscillatory, all right, to be something like that. Okay, but you see, with the damping, if the value is either CCR, C is equal to critical, or if it is equals to, is even greater than the critical value, then the motion is not periodic and is not oscillatory. And here we are giving for different values. So the behavior is almost the same, but depending on the value of damping, the damping coefficient, we are going to see what this value means. So don't worry at this stage. So we are saying this is critically damped, these are overdamped. So we just displace, the motion will be just that it will decrease exponentially and come back to the resting position without experiencing vibration. Okay. So, but how about the underdamped system? Underdamped system is when C, or the damping coefficient, is less than the critical value. So the damping is still less than the critical. So it's not going to stop our motion immediately because they have not attained the critical damping value. So yes, it's going to damp our motion. It's going to reduce the vibration aspect, the oscillatory aspect, but it's not going to stop it just at once. the motion will not be the decrease in vibratory motion is not going to be exponential like that, but we are going to have a case whereby the motion continue reducing until it finally stops. And that's why we are saying the expression under the radical is negative. The value under the square root. You see this value, the C over 2m is the one that is starting, but for this value under the radical to be negative, it means this value, C over 2m, this factor is less than K over m. So that's why you are saying in this expression now, I have interchanged K and M, the position have changed. And then, because the value will be negative, the square root, of course, you know the square root of -1 is equals to I. So that's why we have now the I factored out. And then we have the square root, we interchange the values. Now we want to simplify our expression and we utilize this expression, the Euler's equation, where we are able to relate the exponential function with the trigonometric functions. Okay. So, and this is the expression. I, of course, is the root of -1. So now we can be able to substitute from equation this is a solution. We can substitute to our general solution, which we are calling equation 28, because this is the general solution of our equation for free damped vibration. So if we substitute equation that one into 28 and we utilize this Euler's equation, we are going to get the general solution as this. So the constants A and B, they are called the redefined constant of integration. Of course, a constant is a constant, but of course, if we say 5, if a constant is 5 and another one is 10, of course they are constant, they do not vary, but the magnitude is different. So that's why we are saying, remember we had talked about this constant of integration, C1 and C2. We have just redefined because we know maybe this A is equals to twice the C1. So that's why we are talking of redefined constant of integration. And then now here we have omega, our damping frequency. Now we introduce a subscript D to say that is the angular frequency or the circular frequency for a damped system. So now you see we have got the expression, the solution to our equation of motion for a damped system. So again, from this equation, this is the expression for the damped angular frequency. The value that I was showing you in the previous graph, this is a Greek letter, xi. We call it the damping ratio, and it's expressed as C over C critical. This should be the critical damping coefficient, C subscript CR. We utilize this to simplify the expression here. Of course, this is about working out using what we have derived earlier. Remember we said the undamped natural frequency is equals to this over K over M, the root of that. And then C over C critical is equals to damping ratio. I'm taking you back here. Remember, this is the critical damping system. This is where we are able to derive the expression for critical damping coefficient in terms of the stiffness and the mass. So we are utilizing equation 30 and the other equation we derived earlier to be able to have this expression here. So we are saying the constant of integration A and B, the one we gave in equation 32, these one are calculated or they are evaluated from known initial condition. That is, at t is equals to 0, we have the initial displacement is known and the initial velocity is known. So if you substitute these values in equation 32, our solution equation, you are going to get the values of A. So we are substituting in that solution. We have this expression. Now we have where you have U naught, V naught, all in simplified manner, the trigonometric function. So that's why we are simplifying our expression to this format, where value C is given by this expression. So now we have the alpha and the value C, where alpha is the phase angle. If you look at motion like this deviation from the origin, we call it the phase angle. So if another motion starts at that point, we say that the two of them are out of phase by this magnitude, alpha. So now here I show an illustration for a damped single degree of freedom system with an initial displacement of U naught at an initial velocity of 0. So this is the initial displacement. Okay, if it was starting at the origin, of course the initial displacement would have been 0. Remember, the y-axis is the displacement, then the x-axis is the time. For a damped system, we are going to have an oscillatory motion. It's periodic. Okay, you see one cycle heads here. It's occurring at the same interval of time. So this time T1 is the same as time T2. So it's oscillatory and periodic. What happens is that the amplitude decreases with time. So you see for the first cycle, the initial amplitude U naught, then this, if you call it this U1. So you see U naught is greater than U1 and continue decreasing until our motion comes to rest. And this is typical. This is the most common type of vibration you'll be experiencing. Remember the other one we are saying undamped, that is in an ideal environment. But for actual structure, of course, there will be damping. There will be because of the friction, the joint or the material, or even the fluid, the airflow. The motion has to stop at one point. That's why after an earthquake, the shaking just happened and then it stops. One thing that stopped the earthquake, why it stops very suddenly, is because the stiffness of the structure. The structure is very rigid or stiff. If you had a very flexible system, then it could continue vibrating or oscillating for an extended period of time. The damp period, T damped, the time for one cycle, is given by 2 pi over omega. Now, omega that we are using here is the angular frequency, the damped one, which we derived in equation 34. So here I just wanted for you to visualize between the undamped, the one that we talked in our second lecture about the free and damped. So when it's undamped, you see the motion continue to be the same. The amplitude remains the same. So you see U naught and U1 like that is the same. As the damping ratio increases, continues to increase. So this is for this kind of a motion. You have a spring suspending 10 kilograms of mass with a stiffness of 10. So as of course, the damping ratio varies. So you see the motion continues decreasing until now. What we kind of have here, we are almost going to the region of critically damped. So that now the next motion, if we increase the value of damping ratio, so we are going to have non-oscillatory motion. This is the significance of the damping ratio, what they do to our motion. Let's see how we can estimate damping in structures. Again, I repeat the graphical representation of an underdamped system. And now I'm showing where now we have the initial displacement U naught is equals to 0. So you have U1, the second peak after the second cycle. This is U2, and then continue decreasing U3 like that. So you see U1 will be greater than U2 like that, greater than U3. Again, after one cycle, we have the first period TD, the second cycle twice 2D like that, because we say this periodic occurring at the same interval of time. So of course, after the half quarter cycle, the period is TD over 4. Half cycle at this point, you see the amplitude continue decreasing, and we talk of logarithmic decrement. This is the rate of decay of amplitude of motion, and is given by delta is equals to natural log of the first and the second amplitude. This is an exponential curve. Although in practice, if you plot this curve here, so you see our expression at the maximum point, TD over 4, this is usually 90. So when this part is equals to unity, is equals to 1, this part collapses. Of course, it becomes 1. Then we are left with this part. And this represents the peak. The tangent point, this point corresponds to when the factor cos omega d minus alpha is equals to unit. And this corresponds almost to the point of maximum amplitude. So as you can see here, the maximum point is here, but the curve is slightly, this exponential curve is slightly toward the right. So that's why we are saying it's almost, but the difference is almost negligible. So we assume that at the maximum point, we have this expression expressing this point, and this gives this exponential decay curve. So why am I talking about this? Why am I explaining about this? Let's see to the next slide. So you have seen about the logarithmic decrement. So from this expression, this is a simplified. So we say when our motion is at the peak, so we do not have this part, it becomes 1. So we are talking about this coefficient CE raised to power negative xi omega t. So for the motion, for the amplitude U1, of course, that's when t is equals to 1. For this U1, that's when we have T1. And then U2, of course, this is T1 plus the period. That is maximum point, we say this at time T1. So the next peak will occur at the time T1 plus the period after one cycle. And that's why you can see the next peak will occur at this part, and this part corresponds to, this is 1 1/4. So this could be 1 1/4. So this could be 5 over 4. So what I want to say is 1 1 1/4, and the initial time, this is the time here. Let me repeat again. The time here T1 at this peak is equals to TD over 4. Okay, then plus TD. We said the next peak will occur after one full cycle. So after one period. So this is 1 1/4. This is TD. So, and you can see here, this is why I'm saying from this point, this is TD and this is 1/4 of period, because we know from here to here, that's a whole period. So you can divide it into 4 times. This is the expression for U1 and U2. And remember now, we said the logarithmic decrement. That is the decline in the amplitude of our motion. You remember we are trying, why are we concerned with the amplitude? Because we are trying to track the damping of a structure. So you want to see at what point now the amplitude becomes 0. Once the amplitude becomes 0, is like our motion have been totally eliminated, like there is no vibration again. The structure is not vibrating. So we are tracing. We want to know after how long does our structure, does the damping stop the motion of our structure. So this is the expression. So if you substitute, this value here and this U2 here, you're going to be left with this expression. And again, by substituting the expression for damped frequency, equation 40, TD is equals to 2 pi over omega, the square root of that, you are going to be left with this expression for the logarithmic decrement. So you can see, as once we know what is the damping ratio, the C of a C critical, we can be able to estimate what is the logarithmic decrement. Now, for very small value of the damping ratio, xi, we can approximate this part. If this is very small, let's say like 0.01, then you square that. So this part will almost equal to 1, because it'll be like 1.0001, like that. So you take the square root of that is equals to 1. That's why we are saying for very small value of xi, delta can be approximated by this expression. I would like to go to the examples, but before I go to the few examples, I would like to know whether they have any question. It's a person who is asking, how is the motion periodic yet the value of u is decreasing? What is the definition of a periodic? Periodic motion is a motion that occurs of a repetitive in equal intervals of time. Okay, this is the definition, that a periodic function is a function that repeats its value at regular interval. For example, a trigonometric function which repeats at a period of 2 pi rad. Periodic functions are generally used to describe oscillations, waves, and other phenomena that exhibit periodicity. And any function that is not periodic is called a periodic. If a motion is repeating itself at regular intervals, but the amplitude is decreasing, is that motion periodic or aperiodic? If nobody else within the comment or concern, or somebody can add something to that, then let's see how do you apply these expressions. So let's look at the examples. So you have a vibrating system which consists of a weight of 50 newtons. So under spring stiffness of 4 newton per millimeter. So we have maybe something like this. So we have that as a spring. Then we have this as 50 newton. Then we know K here is given as 4 newtons per millimeter. And the ratio of two successive amplitude. The motion is damped, so it have this damping component. The ratio of our motion is like this. So the initial amplitude is higher, continue decreasing like that. So we are saying the ratio of, maybe this is U1 and this is U2. So we are saying U1 over U2 is equals to 1 is to 0.85. So the first thing that we need to calculate is the logarithmic decrement. This is direct, straightforward, natural log of U1 over U2. So use that ratio, we get the logarithmic decrement. The damping ratio, xi, is given by the equation 44, the delta over 2 pi. The third is the damping coefficient, C, the square root of this 2 pi, xi, the square root of km. By the way, could you confirm? I realized there could be some error here. Could you confirm that this is the actual value here? Note that you have to be very keen about the units, so that you have a constant or uniformity in the units that you use. If you are given this one in terms of maybe kilonewtons, and then these are millimeters and like that, we have to convert them when you are doing your multiplication. Then we look at what is the natural damping frequency. This is the expression. So you just need to first calculate the undamped. This is undamped natural frequency, and we know weight and the acceleration due to gravity. That one gives you the undamped. Therefore, now damped is, you substitute for that. This one, the damping ratio, we calculated it from the previous slide, number C. So you get it as 28 rads per second. You can see the two values are almost the same. Let's look at another example. So you have a platform which have 18 kilonewtons. It's supported by 4 equal columns. So from one side, we can only see 2 columns, which are clamped at the foundation. Clamped tells you that this is a fixed support. So from experiment, it has been noted that if you apply a force of 5 kilonewton, a displacement that will be experienced from that is equals to 2.5 millimeter. F is equals to A, the displacement or deformation. So we have the force, a force of 5 kilonewton. We have the spring stiffness, which we do not know, is brought about by a displacement of 2.5. Remember, this is 5 kilonewton. This is millimeter. So you have to convert it to newton by multiplying by 1,000. So again, you are given, it is estimated that the damping in the structure is in the order of 5%. This is the damping ratio. So you have to compute the undamped natural frequency, damping coefficient, logarithmic decrement, and the number of cycles to take the amplitude, the motion, or the amplitude of the motion from the initial value of 2.5 to 0.25. So let's see. A, what is the undamped natural frequency? Of course, we have the expression. So what we are being tested here is how to calculate K. This is what I was trying to calculate the previous slide. We have the static force and displacement, so you can be able to get the static stiffness as 2000 Newton per millimeter. Therefore, our undamped natural frequency is given by that. So the damping coefficient, the C, is equals to, this is the expression we derived earlier. So it's just a matter of substituting, and we have the damping ratio. And then now Km, you have K, and then M expressed in terms of Newton. That's why I'm multiplying by 1000 divided by the G. So remember, what we are given is weight. So that's why we are dividing by G to get the mass. So again, we have that is the damping coefficient. So I didn't work out this one because I was just punching with my calculator to confirm the answer. Then again, logarithmic decrement. Now, since we are not given any other information, if you look at your question, you look at all the data that you are given. So you find like we are not given any other information. So we can only estimate the logarithmic decrement. So we assume that this value is very small, such that we can be able to estimate 2 pi. Actually, we can even be able to calculate the action, because from this expression we have this value. Again, this is what we are saying. You can try to calculate when you substitute this value, because this will be 1 minus 0.05 squared. You can imagine if you square this, how many decimals? Then 1 minus that square root is almost 1. So you can compare between when we calculate the approximate value or the actual value. So you include that part, 1 minus xi squared. You see whether to be very different from this value. Finally, part D, we want to know the number of cycles and time required for the amplitude of motion to reduce from an initial value of 2.5 to 0.25. So again, just as an illustration, we have the motion will go like that, decreasing like that. So you want to know if the initial value was 2.5. So it means our motion is like this. We are starting with an initial displacement. So initial displacement is not 0. So we are starting with an initial displacement from that point. So like that. So you want to know from this initial value, u naught, which is equals to 2.5, after how many cycles are we going to get to a displacement or amplitude of 0.25? The ratio between the first amplitude u naught and the amplitude un after n cycles is equals to u naught over un, which is equals to u naught over u1, the dot product, u1, u2, u2, u3, u3, u4, until un minus 1 over un. Now, if you take the natural logarithm, you are going to get u naught over u1, u1 over u2, because we know the logarithmic decrement is equals to un minus 1 over un. That's why I was talking about u1 over u2, u2 over u3, that is another logarithmic decrement, u3, u4, and it's constant. So that's why we are saying now, if you take the natural log, so depending with the number of cycles, n cycles, we are going to have n delta. So natural log, we have the initial displacement, you notice 2.5. The final that we want to achieve is 0.25. This is equals to n. Our logarithmic decrement we have calculated in the previous calculation, the part C, as 0.314. So we can get n as 7.33. So we can't have point cycles. So we say the next whole number is around 8 cycles. So the time for 8 cycle is equals to 8 times, because the period is the same, the interval for our motion, one cycle finished with the same time period. So we need to calculate the damp period, which is given by this expression or this expression. And we have already calculated what is this part, what is this. So after 1.52 seconds, we can comfortably say that our motion is going to reduce. The amplitude is going to reduce from 2.5 to 2.5. So I have given one small exercise. You can look at it. Again, probable answers. These are answers based on what I had calculated. So you can confirm whether it's correct or not. Then again, there are some examples, 2.1 to 2.3, that I have given in the main reference text in our book. So go through those examples, then you'll be able to gain more experience in applying this equation that we have had. Good. That marks the end of my lecture for today. So now I'll welcome some questions and comments.